We're talking about series. We've basically been focusing on finite series so far. But there are also infinite geometric series. And when you have an infinite geometric series, that means it just goes on forever. On and on and on and on and on. Okay? So you can see that in this one here, this one on the left, we have 1/2, 1/4, 1/8, 1/16, 1/32, and so on. And since the denominator is getting bigger and bigger all the time, the fraction's getting smaller and smaller. Okay? And then on the one on the right, we have 1/32, 1/16, 1/8. So the fractions, the denominator is getting bigger all the time, which means then the fraction's getting larger. Okay? Or I should say the denominator is getting smaller. Getting smaller all the time, which means that the fraction is going to get bigger. So these are two different types of partial sums. And we graph them. The one on the left is going to come up, and as the fraction gets smaller and smaller, the sum is actually approaching a specific number. Where the one on the right, because the fraction keeps getting larger, then the graph is going to keep going up and keep getting bigger and bigger. So when we are adding them together, the ones on the left, as the fraction gets smaller, those are actually doing what we say they are converging on a specific number. Where the ones on the right are going to diverge because they're going away from zero, basically, okay? Getting bigger and bigger and bigger, not getting closer to a specific number. So we have two different types of infinite geometric series. We have ones that converge, and when they converge, the value of r, the absolute value of r is less than 1. So it's between 0 and 1. Okay? And we say that those have what's called a limit. And so for those of you who go on and do calculus someday, you'll talk about limits when you get into calculus. And basically all that means is that the numbers are getting closer and closer to a specific value, okay, a specific limit. Okay? So the series that converge, their value of r, their common ratio, okay, the absolute value is going to be less than 1, so that's the value of r is between -1 and 1. If the series diverges, then the absolute value of r is greater than or equal to 1. So in the one on the left up here, S sub n, the value of r was 1/2, less than 1. It's converging to a specific number. The one on the right, the value of r was 2, because these are doubling each time, and so that was diverging. So we want to tell whether a specific series converges or diverges. And these are specifically geometric ones, so we know that there's multiplication going on to get from one term to the next. So the first thing we want to do is we want to determine what the value of r is. Right? So what am I multiplying by each time? What's my common ratio to be able to get from one term to the next? So letter A, what are we doing there? To get from 10 to 1 to 1/10 to 1/100th, and so on. What are we multiplying by? RJ, what are we multiplying by? How do I figure it out if I'm not sure? You use your calculator, okay? And divide. Take the next number and divide the previous number. What's 1 divided by 10? Okay, 0.1 or 1/10. All right. So, is that value of r less than 1 or greater than 1? Less than 1. So then that means that it's going to converge. So remember, to find out what the value of r is, we just take one term and divide by the one next to it. Doesn't matter which ones you use. Any two work. Letter B. Danny, what's the value of r? 3. Is that less than 1 or greater than 1? Greater than 1. So that means it's going to diverge. When it converges, it has a sum. When it diverges, it does not. And these are infinite geometric series, and in the next example, we're going to look at how to find that sum when they do have one. Getting bigger, diverges. Getting smaller, converges. Okay. All right. So here is the formula. Here it shows how they find it, all right, how they got this formula. But here's the formula for an infinite geometric series to find the sum of those numbers. All right, so we learned how to find the sum of a geometric series. So that would be a finite one. Here we're talking about an infinite geometric series. How do we find the sum? And one specific thing is that r must be less than 1 because it has to converge for there to be a sum. If it diverges, there's not a sum. What? That's a comma. That's just a comma there. Sorry. So it's just s equals a sub 1 over 1 minus r. Right? And where a sub 1 is the first term then. So we start out and we find r. So we take two terms and divide them. Right? I'll take the first two. Pretty easy. R equals negative 0.2. Is the absolute value of negative 0.2 less than 1? Okay, so it converges. All right, so we're good. That means it does have a sum. So to find the sum, I just plug it in. The sum equals the first term divided by 1 minus the common ratio. And this is actually 5/6 or 0.833, I think it is. So even though they alternate positive and negative, it's still getting closer and closer to a specific number. Yes? That it diverges and there is no sum. Okay? If r is greater than 1, we say it diverges and there is no sum. because the numbers just keep getting bigger and bigger, so they're not converging to a specific number, they're going to infinity. Or if in this case, if they're positive or negative and they're diverging, it's just jumping all over the place then, from a positive number to a negative number to positive, negative. All right? Letter B. Now I know this is an infinite series because of the infinity sign. Okay. Could I put that in my calculator? And the question is, and to my knowledge, is no, you can't, because you can't put infinity in your calculator. Okay, there is no infinity symbol here anywhere on this screen to be able to do that. Okay.
What about all the other screens?
What?
All the other screens on the button tickets to different screens, and those different screens have different things.
They do. Good luck. Okay? All right. You search to find it. And if you find it, you let me know.
Okay.
All right? Okay, so what we need to determine then is what is the first term and the common ratio. The common ratio for in summation notation is just the number that's being raised to the power. What's being raised to a power here? 1/2. So R is 1/2.
Number being 1 because k equals 1.
Well, not because, right. Okay, how do I find the first term then? How do we find the first term? Okay, yep, we put in 1 for k. So the absolute value of 1/2 to the 1 minus 1 power. And since 1 minus 1 is 0, what's the absolute value of 1/2 to the power of 0? What's anything raised to the power of 0? 1. Okay, so this is 1. So to find the sum, 1 divided by 1 minus 1/2. So that's 1 divided by 1/2. What is 1 divided by 1/2? And this is why we did that question number 1 in the warm-up. Okay, divided by a fraction, we're supposed to do what? Copy, change, and flip. So 1 times 2 is 2. All right, so one of the things to understand is that when we're doing these infinite geometric series, if they're going to converge, most of the time they're not going to converge to a real big number. You know, we're not talking 500 or 800 or something like that. All right? Because since we keep adding smaller and smaller and smaller numbers, then it's not increasing very fast then. Okay? That's actually, if we were to do, Jake asked us about number 34, from the homework. All right? Hey, that was an infinite geometric series, wasn't it, if we would have kept going? All right? So eventually, that's going to level off somewhere, okay? And we could figure out, all right, so that person's only going to go so far if they keep doing that. Because, eventually, how far he's going in one day is about that far. Right? I mean, if he went 10 feet one day, then he goes 5 feet, then 2.5 feet, then 1 1/4, and then, about 1/2 foot, and then less and less and less and less. So, okay. Example here. Okay. The last example is the hardest one. Okay, as usual. But actually, it's very easy. Okay. So this is one of the easiest lessons that we've done this year. Okay, because those first two are pretty easy, right? Okay. This is really easy. Now, there's a very long, drawn-out way how to do this. All right? But I'm not a big fan of that long, drawn-out way how to do this, because this is really, when you have repeating decimals, that it's really an infinite geometric series. Okay? But what we're going to do is do this the easy way. You like the easy way, right, RJ? Okay. All right. How many numbers are repeating here? 2. Okay. 6 and 3, right? Okay. So to find the simplest form of this repeating decimal, we take 6 and 3 and put it over the number of 9s. Okay. Excuse me. Let me rephrase that. That however many numbers repeat, you're going to use that number of 9s in the denominator. Okay? So I have 2 numbers repeating, so I'm going to put 2 9s in the denominator. And then I simplify the fraction. And that's all you got to do.
So that was the hardest thing.
No, I was being sarcastic.
Oh.
Okay?
So
So,
it's like,
however many numbers repeat, you put that many 9s in the denominator, simplify the fraction. Okay, so 63 over 99 simplifies to 7 over 11. So if we have 0.521 repeating, that's equal to 521 over 999. So all the single digit repeaters are just that number over 9. 1/9, 2/9, 3/9, 4/9, 5/9, so on. Okay, think you can do those type of problems? You don't know? All right. Okay. So however many decimals repeat, I put that number in the numerator and that many 9s in the denominator and simplify.
I think this is the fastest way I've ever been done with like a lesson.
It's been a while.